I'm Alexander Holroyd, and this is the Pendulum Wave music machine. In a previous video I showed it in action, and now I'm going to try to explain how it works. As you can see, we have 15 hammers hitting the keys of the glockenspiel, and each hammer is actuated by one of these 40-tooth gears, as I'll explain in a minute. Each hammer has built into it one of the rubber Technic bumper pieces, and that means that the hammer has some flex to it, so it's able to bounce back and lift off the key to allow it to resonate better. And in addition, each hammer rests on another of the rubber bumper pieces, and that gives it a soft landing so it doesn't create extra noise when it lands. So the keys are actuated by these Technic ball joint pieces in the 40-tooth gears, and I experimented quite a lot finding the right system for this, because it's there's only 2 studs of width here, and it's important to find something which cannot catch on either side and which also cannot catch on the white clutch gear here. So these ball joints work quite well. So how does the gearing work? So the rotation speeds of these gears are very, very specific. They rotate in the rotation speeds are in the ratio 81 to 82 to 83 to 84, all the way up to 95. So what's important here is that these are whole numbers and they're equally spaced, and they start off with all the hammers synchronized so that they strike at the same time, and then as it goes on, they gradually get out of phase, and this produces all the musical effects that you hear. And right now it's just about at the halfway point, so the odd-numbered, or rather the even-numbered gears, number 82 and 84, 86 and so on, have all made a whole number of rotations from the start, and the odd number of ones have made a whole number of rotations plus a half. So that what that means is that the odd number of ones are almost synchronized, and the even numbered ones as well. So we get all of those together, and all of those together. And it's very important that I have these white clutch gears built into the drivetrain, because this allows the positions of the gears to be adjusted very accurately, and that's important so that all of them strike at exactly the same time. And now I will try to explain the gearing ratios. So as I said, the ratios are 81 to 82 to 83 to 84, etc. So that means that in the time it takes this one to rotate 81 times, this one rotates 82 times, and in the same amount of time this one rotates 83 times, and so on. So if you had arbitrary gears with arbitrary numbers of teeth available, it would be very easy to achieve those gear ratios, but Lego gears only come in a few sizes, so instead I had to do this using differentials. So each of these red pieces here is a differential. Differentials are usually used in vehicles in order to allow a vehicle to have 2 driven wheels which go at different speeds when it goes around a corner, but here they're being used for arithmetic with speeds. So how does it all work? Well, all the power just comes in this one axle at the top, and in the video that was driven by a Technic L motor, which I actually placed on the end of a very long axle in order to reduce the noise from the motor. So the power comes in here, and here we have a 1 to 2 gearing ratio, and here we have a 3 to 5 gearing ratio. So the result of that is that the relative speeds of this and this are in the ratio 5 to 6, so that means this rotates 5 times in the same time that it takes for this to rotate 6 times. And then the first thing we encounter is a differential, and a differential averages the speeds of the two side axles. So in this case, this side axle is going at speed 5, and this is going at a relative speed of 6. So the relative speed of the outer casing of the differential will be the average of those two, which is 5.5. And it's going to become easier to do the arithmetic if we just multiply all these numbers up. So this original ratio of 5 to 6, if we multiply both of those numbers by 16, that's the same thing as a ratio of 80 to 96. So that's what I'm going to use. And then if I say it that way, then this first differential has relative speed, the average of 80 and 96, which is 88. And now all the other gearing that you see over here is just one-to-one gearing, like this, where the gears are the same size, and differentials. So there are no other gear ratios except for these two at the start. So what happens next? So if we go over here, this was speed 80, so this is still speed 80, and this is one-to-one gearing, so speed 80, 80, 80, 80, and same over here. So if we look at this differential, then this side shaft has relative speed 80, and this one has 88. So this differential rotates at the average of those two speeds. Average of 80 and 88 is 84. And then over here we have 88 from before, and we have 96 on the right hand side. So the average of 80 and 96 is, the average of 88 and 96 is 92, so that's the speed of this one. And then as we come down, we have another row of differentials, and by the way, you might wonder about the directions that everything rotates, because when I have one-to-one gearing, of course I reverse the direction, but it turns out that doesn't matter because everything is in levels, so when I move to another level, everything rotates in the opposite direction to the previous one. So yes, on this next level now we have, well, let's start over here, we have this differential. This side shaft has relative speed 80, and this we calculated before was 84, so the average of those two is 82, that's the speed of this. And now we have 84 from here and 88 from here, so this has speed 86. And then similarly the average of 88 and 92 is 90, and the average of 92 and 96 all the way over here is 94 for that differential. And then finally we have one more row of differentials, which again just splits all the differences. So we have relative speed 80 from here, and on the other side we have relative speed of 82 coming from this differential casing. So this one has speed 81, relative speed 81. And so it goes on 83, 85, 87, etc. So this actually gives me 17 gears from here to here with relative speeds 80 to 96, and I don't use the two outer ones because I only have 15 keys on the glockenspiel, so the outer ones are ignored, and then everything else just comes down here. With everything has a 1 to 5 gearing ratio involving these clutch gears. And a few more details of the construction. When I first came up with this idea, and when I made the smaller 1 octave version, the spacing was wider. I had a spacing of 5 studs per hammer, and that wouldn't have worked for this because it would make the whole thing much too wide. It wouldn't fit on the glockenspiel properly. So I thought that was the minimum because each differential is 4 studs wide and you need supports either side for it, so that makes 5, but then I found this way of arranging things with 2 differentials right next to each other like this, which makes everything 1 stud smaller per hammer. And a few more details. As you saw, I have this lift arm that lets me lift up all the hammers at the same time, and on the underside I have yet more of these rubber Technic bumpers acting as feet, and that just reduces the vibration noise a little bit. So this was the Pendulum Wave music machine. Thank you for watching.